In this tutorial, we will investigate the simulation results we found from Tutorial 1 and use the DWSIM Utility tool to compare the binary phase envelopes calculated by using different property packages. Next, we will resolve the simulation using the new property packages. Then we will use the DWSIM optimization tool called sensitivity analysis to adjust the molar flow of ethanol into our mixer and view its effect on the outlet temperature of the mixer. Finally, we will set up a simple splitter and use the DWSIM adjust object to create a 10 gallon per minute stream with an approximate volumetric fraction of 10% ethanol. Let us begin by double-clicking the DWSIM shortcut icon on your desktop. This will open the DWSIM startup screen. From the Recent Files section, you should see the simulation you created in Tutorial 1. If you have not completed Tutorial 1, you may want to do so now. Left-click the file to open it. I named my file Tutorial 1. Please allow me a second to fit the Applications window into my recording viewport. Notice from the property table the temperature of the stream exiting the mixer. Even though our simulation gave us no warnings or errors, the heat of mixing calculated for this adiabatic mixing process seems suspect. So we will use the DWSIM binary phase utility to view how the Ping-Robinson property package is calculating the phase equilibrium data of water and ethanol. Do this by selecting Utilities and clicking Binary Envelope. When the Utilities form appears, select Mass Fraction for the x-axis basis and click Calculate. Notice how our phase envelope has an irregular shape and varies substantially from our reference chart, which was created using experimentally determined data points. Now close the utility window and open the Configure Simulation form by clicking the icon that looks like a little Lego piece. Click the Basis tab, and with the left click of your mouse, select NRTL from the available property packages and click Add. Also, add the Uniquake property package to the simulation environment. Now close the Configure Simulation window and reopen the binary envelope from the utility options. Again, change the x-axis basis to mass fraction, but this time check the Compare Models option and click Calculate. Notice how both the NRTL and the Uniquake property packages give appreciably better results than the Ping-Robinson property package. However, neither package would be expected to yield the highly accurate results needed for the design of an industrial application, such as a distillation column. And in a later tutorial, we will use DWSIM to perform a regression study of experimentally obtained data points to adjust our interaction parameters and give us a much more accurate thermodynamic model. For the purpose of this tutorial, we will change our property package to the Uniquake and use the Uniquake model. Since this will give us a reasonable approximation of the distillation column we will be configuring in a future tutorial. So do this by exiting the Utilities window and opening the Configure Simulation form. Select the Basis tab if it is not already selected, and in the Selected Property Package is section, highlight Ping-Robinson and click Delete. Do the same for the NRTL package. With the Uniquake property package highlighted, click the Configure button near the bottom of the window. When the Configure Property Package form appears, select General Options. Scroll to the bottom of the list, and next to the enthalpy calculation method, type in 0 for the value. This will tell the simulator to use the Lee-Kessler method to calculate enthalpies. Now close the window and also close the Configure Simulation window. From the Calculator section on the Quick Access toolbar, click Play if it is not already selected, and then click the Recalculate icon. Notice the results of the mixing calculations are still showing this as an endothermic process, which seems counterintuitive. So we will use the sensitivity analysis tool to see if changing the molar flow rate of ethanol into the mixer will change the outlet temperature. This will not validate our results, however, it will let us see if the Lee-Kessler enthalpy calculation method is predicting an endothermic heat of mixing throughout the entire range of different ethanol water molar feed ratios. To do this, click on Optimization and select Sensitivity Analysis. The Sensitivity Analysis form should appear. Select the Sensitivity Studies tab if it is not already selected, and in the Case Manager section, click New. DWSIM will automatically name the new simulation case. You may change the name if you'd like. In this case, I will leave it with its default name. Now select the Independent Variables tab. Then select the variable which you wish to adjust by using the drop-down list next to Object. DWSIM allows you to simultaneously adjust up to 2 different object properties. However, in this tutorial, we will only be adjusting one. Since I want to adjust the molar flow of ethanol into the mixer, I will select the ethanol inlet stream. And for the property, I will select molar flow. Leave the lower limit at 0, and for the upper limit, type in 500. And for the number of points, type in 26. Now select the Dependent Variables tab. In the Add Remove Variables, click the little green icon that looks like a little plus symbol. Then, under Object, select Mixer Out, and under Property, select Temperature. DWSIM also allows you to evaluate an expression using multiple properties from the flowsheet. However, for this case, we will leave that option unchecked since we are only interested in looking at the temperature of the mixer's outlet stream. We are ready to start the analysis. So open the Results tab and click Start Simulation Analysis. After the analysis is complete, DWSIM will automatically restore the simulation to its original state it was in before the analysis was initiated. The Sensitivity Analysis module is a powerful tool that allows users to view how the changing of 1 or 2 process variables can affect very complex systems as a whole. The module also allows you to quickly plot your results, which is extremely handy. So let's plot the analysis we just ran. Open the Chart tab and click Draw. Notice how the outlet temperature of the mixer changes as we change the molar flow rate of ethanol into the mixer. Now that we looked at how the sensitivity analysis tool works, let us close this window. And from the Object palette, click and drag a splitter onto the flowsheet. Also drag 2 more material streams onto the flowsheet. Name one of them Mash and the other Reject. Remember that we want DWSIM to calculate the properties of these streams, so we will not specify any values into the streams themselves directly. Now hover over the stream we just named Reject and right-click. From the options that appear, select Invert Horizontally. This will change how the stream appears on the flowsheet. Now select the splitter, and for the inlet stream, select Mixer Out. For the outlet stream 1, select Mash, and then Reject for outlet stream 2. Under the parameters option next to operation mode, use the drop-down list to select stream mass flow spec. And next to stream 1 mass flow spec, input a value of 645 grams per second. This should give us an approximate flow rate of 10 gallons per minute in the mass stream exiting the splitter. Now we will use the Adjust object from the Object Palette window to adjust the molar flow of ethanol entering the mixer so that our mixer outlet stream has an approximate 0.033 molar fraction of ethanol, which should equate to roughly 10% volumetric fraction of ethanol in our mixer outlet stream. Do this by dragging the object onto the flow sheet. This object looks like a red circle and has the letter A inside of it. The Adjust object should be selected by default once it's dropped onto the flow sheet. If it is not, go ahead and select it. Now, in the Properties tab of the Selected Object window, expand both the controlled variable and the manipulated variable. Now, next to Controlled Variable, click where it says Click to Select and select Material Stream, Mixer Out, and in the section labeled Variable, scroll down until you see Molar Fraction, Overall Liquid Phase, Ethanol. Select it and click OK. Excuse me. Now select the variable you wish to adjust in order to achieve your desired outcome. In this case, we will adjust the molar flow of the ethanol inlet stream. So find the correct stream and then the correct property, select it, and click OK. Now, in the value fields labeled minimum and maximum value, leave the minimum value at 0 and set the maximum value to 50. This will limit the range of manipulated values the Adjust block will use when trying to search for a solution that meets the parameter you selected. So now in the parameter section under Adjust Property Value, type in 0.033. Leave the rest of the default settings as they are and click in the empty field next to Control Panel. A little icon with 3 dots will appear. Click it. That should bring up the Control Panel window for the Adjust Solver block. For the convergence method, I found that the Brent method works best for this type of Adjust Solver block. So check next to the Brent method option on the top of the dialog box and then click Start Adjust. If we want our Adjust object to work every time we change a flowsheet property and recalculate the simulation, we must change the value next to Simultaneous Adjust from false to true. Now test that the Adjust object is working by increasing the molar flow of water that is entering the mixer. I will increase the molar flow from 50 to 60 moles per second. If your simulation calculator is in play mode, the simulation should automatically solve after you change the value and press Enter. If not, click the play button and then click the Recalculate All button. Now let's look at the mixer outlet stream to see if we have achieved our desired effect. Select the mixer outlet stream and under Conditions next to Composition Basis, change the value from molar fractions to volumetric fractions. Under the volumetric composition section that appears, click the arrow next to Mixture in order to expand it. We can see that our volumetric fraction of ethanol is now approximately 0.1, which is of course 10%. Now hover your mouse over the stream named MASH and view the properties that appear and look at the volumetric flow. This should be approximately 632 centimeters cubed per second, which is roughly equivalent to around 10 gallons per minute. You may choose to save your project at this moment, as this will be the starting point of a future tutorial. This concludes tutorial 2. If you have any questions, leave them in the comments below, and I will do my best to answer them. Thank you for watching, and subscribe for more upcoming tutorials on DWSIM as well as other open source engineering softwares.